Hello, everyone. I guess we'll get started. My name is Hugh McKee. I'm a developer advocate at Lightbend. Lightbend's the company behind Scala. The Scala programming language is also the company behind Akka, the Akka toolkit, and Play, the Play framework, and another framework called Lagom, which is a microservice framework. But today I wanted to talk to you about a couple of my favorite topics. One is Akka. I love Akka. This is why I work at Lightbend. I lucked into, actually stumbled into Akka in a Coursera class. I was taking a Coursera class on Scala, and at the end of the class, we came across Akka, and it was like, for me, the heavens gates opened because we had this problem that we're working on, and it turned out that Akka was the perfect solution for it. So I saw it, and we were able to take it right away and put it into a project, and I was just amazed. And then a newer favorite topic of mine, and I'm really delighted to see that there were a number of talks already at this conference about event sourcing CQRS. In fact, the talk just before this one in this room was about that topic. And the more I'm getting into it, the more I'm working with customers, the more I'm kind of internalizing it myself, the mechanics of event sourcing in CQRS, the more I'm liking it, because my background was in enterprise IT. And in my bio, I actually say I've got years of experience building brittle systems that failed too often, something like that. My career was building systems that went down, and I was doing production support as well, and it was painful, and I hated it. And it's like, man, I do not like building software systems that freaking go down. It just drove me crazy. So actually, the motivation for us that where we eventually used Akka was we had this system that was very important about 10 years ago, and it was brittle. It was a big system. It was kind of our own early cloud invention, and it was running on like 100 or 200 servers, things like that, and this was kind of the controller piece. When this controller piece went down, the whole cloud went down. It was really embarrassing. And all the users of this tool, were very unhappy with us. So we were desperately looking for something to solve it. This solved it, and man, that's where I was bought in. It was like, finally I can build a system that can keep running and take a hit. To me, event sourcing in CQRS takes it a step further. It's like, okay, now there's a real concrete architectural feature that I've done other talks on this, and I'm working on another one where I just want to praise the capabilities of event sourcing in CQRS. I know that, and we'll go into it in a bit, but this is a controversial topic. Even within Lightbend, I've had very intense, I'll say, conversations about the merits of, or should we push it, should we not push it, things like that. But to me, I just see it as a way to build systems that are reactive. They're always responsive, they're resilient, and they can expand when the load goes up. So let's get into it. So hopefully you've already sat in on some of the talks about event sourcing in CQRS. So CQRS is Command Query Responsibility Segregation, and we'll be getting into that quite a bit. This diagram, it's my own version of a diagram I saw on Microsoft. To my surprise, Microsoft has a ton of documentation on event sourcing in CQRS. Really, really high quality documentation. In fact, some of our documentation links off to their documentation. So if you're looking for another source of information about this topic, Microsoft is a great place to go. So in this diagram, I think it does a nice job of kind of summing up some of the mechanics of event sourcing in CQRS. So starting over on the right, you've got the client, and the client is interacting with some service, and the client is either asking to make some kind of a change, in the terminology here will be some kind of command, or it's asking to do some kind of a query. So depending on if it's a command or a query, things kind of go in one direction or the other. So following with a command, there's this concept of a write side and a read side. So on the right side, a command comes in. The command may be validated. Is this a legitimate command to perform? A command is an intent to do something. Like the example code I'm going to be showing you today is, say, it's a bank account. We're doing deposits and withdrawals. So I want to do a deposit. I want to do a withdrawal. It's an intent. But the right side, when it validates a command, what is emitted from that is an event. And an event is simply something that has happened in the past. It's a statement of fact. It's a piece of history, whereas a command is something that you want to do but hasn't happened yet. So this event then is stored in an event log. And the event log is super simple. It's like a key value. There's maybe an entity ID, maybe some sequence number or a timestamp, something uniquely identify an event, and it's just slammed into a real simple data store, and it's just insert, 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 insert. There's no updates, and the theory of it is there's no deletes as well, because this is a full history of all the changes that have occurred to, say, your bank account. Now, in a bank account, it's actually kind of a bad example, because with bank accounts, you always keep your history, right? You have to. But imagine with an order, for example. With an order, you're adding items, you're removing items, you're adjusting the item quantity, you're adding the shipping address, adding the billing address. So instead of, say, updating a few tables every time you're getting all these changes into an order, what you're actually doing is you're accumulating a series of events. I've added an item, I've adjusted the quantity, here's the shipping address, here's the billing address, or the billing information, this is the customer information. Each one is a distinct event. The aggregate of these things makes up the current state of the entity. And it's the idea of with domain-driven design, for example, which I can't even go into, but the focus there is on events. Events is becoming a very popular way of thinking about how to build systems, from design to implementation now to really building distributed systems. To me, this really enables not only creating microservices or services that are really fast and can run very quickly, but services that can play well in a distributed environment. And I have a whole other talks that I do on that, but here we're going to focus more on the code part of it. So when an event goes in, the general way this works is that the event store, say, could be Cassandra, right? I mean, there's not dictating what databases you use. But the point is that, say, you're just using a very simple data store for your events, but then there's the query side. So the query side is whatever database makes sense for you to do queries. Obviously relational is a good choice, but a document database could be a good choice. A graph database could be a good choice. Combinations of those working together could be good choices. The thing is, though, is that when a command comes in, when the event is captured, you're basically ready to go back to the sender of the command and say, all right, we got it. The process of getting the event over from the write side in the event log to the read side is eventually consistent. It's not a single transaction. I mean, some people you can implement it that way if you want, but this architecture will handle where there's this eventual consistency gap between the write side and the read side. Now, where this really works out well is, say, you're getting spikes. And one of the biggest problems I've run into in the past is that your point of contention is the database. You get slammed with a bunch of transactions at peak load, and the first thing that starts to slow down is the database. And the database can get really unhappy. I don't know if you guys have ever had, we use Oracle all the time, and when we got Oracle mad, it got mean, because it didn't just slow down, it really put the brakes on. It's things like transactions going from, say, 4 or 5 milliseconds to 200 or 300 milliseconds, and it would just kill us. So in this case, all we're doing is writes really, really fast. So we can take spikes. This guy is struggling to keep up. So we could fall behind, but eventually it'll catch up. So you can get a spike where you get, maybe you get a bunch of events that you're ahead, and then on the read side, you eventually catch up. So your read side will always be keeping up with the write side. But the beauty of this is that one of the things it addresses is you're not building or designing a database where you're making compromises between write performance and read performance, right? The simple thing is, like with a relational database, for read performance, you add indexes. But that doesn't help your write performance. So you have to decide every single index that you add, should I add it because it's going to slow us down on the right side? Those types of things. Here, it kind of pulls it apart. This is super fast, super simple. It can just take events really, really fast. And then you really optimize, and this is often denormalized. database. Like if it's a relational database, it's denormalized. It's optimized for queries. So the way you set up your tables or the way you set up for queries is like whatever queries this service is supposed to support, then that database is optimized for the queries. So it's not kind of this trade-off of normalization where you're trying to compromise between the read and write performance. In any case, there's a lot, there's other talks that have been done here. There's a lot of material available on this, and it's a really interesting topic area. So just real quick, as an example, in the event log, the idea is that you're just storing events. So like deposit, withdrawal, deposit, that type of thing, right? And the sum of those events, aggregates up to the state of the entity, the bank account or an order or whatever, okay? Now, one question would be that with a bank account, you have a long history. You could have years of events, right? Hundreds or thousands of events. And when you want to recover the state of an entity, you don't necessarily want to spin through all those events and get them back. So there's a concept of snapshotting, that periodically, in whatever frequency makes sense for the way your system behaves, you save a snapshot, which is a full snapshot of the entity. But you're not doing that like every time. You're doing that like every day or every 100th time or some frequency that makes sense. So when you need to recover an entity's state, you go to the last snapshot and any events that occurred since that, so you can recover it very, very quickly. So really I want to focus on the way we implement event sourcing in CQRS with Akka. So the idea is that with Akka, how many people are familiar with Akka? Wow. You guys are, I forgot to say this earlier, you guys are hardcore. This is Saturday. I was here at Java Day last year. It was Saturday and Sunday was a conference, and it was packed. Here it is Saturday, and you guys are here. It's amazing. You guys are really impressive. You guys are hardcore, man. Anyways, I'm glad to see that so many people are familiar with Akka. So with Akka, the really cool thing with Akka is that the way I look at it is you're not constrained to a single JVM anymore. You can build a system that can scale out to multiple JVMs. And those multiple JVMs are running maybe on different servers or running in different containers. They're distributed across the network. But for us as developers of Akka code, we're really not getting all tangled up with, say, the messaging or the interactions between actors, which I'll show you some examples of in a few minutes, communicating with each other across the cluster. That's all really simple because of the way Akka works. It just, again, when I first got introduced to this and I saw this capability, wait a minute, I'm not constrained to a single JVM anymore. I can run multiple JVMs, and it's like one line of code to send a message from one actor to another, and then I don't have to worry about all the mechanics of all the stuff that has to happen. It's like, okay, I think I like this stuff. So in the case of event sourcing in CQRS with Akka, though, the idea is that each entity that's receiving a command is represented by an actor that has the state of that entity in memory. So say you have a system that's handling bank accounts or orders, and say at the moment there's thousands of orders that are currently active or thousands of bank accounts that are currently active. Then there's thousands of actors, one per entity, that are active across the cluster. So the idea with the cluster is if there's too much to fit in the memory of one JVM, then you can go to 2 JVMs, you can go to 3 JVMs, you can go to 4, you can go to 100, you can go to 1,000. I think often I see people, like in a dozen or, 3 is a good number for resiliency, because not only are you, increasing your processing capacity, but you're also increasing your resiliency, because a part of the way Akka works is, it can handle losing a node. A node goes away because, say the server that it was running on went down, or you want to shut it down because you don't need that excess capacity. The cluster itself can deal with that. I'll show you that in a little bit. The other thing I want to show you here, though, is what's happening. What I'm trying to show in this is that as more commands come in, more entities come to life. They're in memory. But when those entities no longer receive commands, they essentially kind of get bored and shut themselves down just to free up resources. So Not a lot of code to do this. Akka's doing a lot of work for us to make all this happen, but the idea is I've got 6 sample projects that I'm going to show you that kind of build up from simple actors to event sourcing and CQRS, and the last 2 projects, they're all on GitHub, that there's not a lot of code involved in doing this. So these are all running examples that you'll be able to play with if you're interested. But this, again, is the big payoff. Say this node goes down, the things that used to be running on that node that went down are, it's like no problem. Akka kind of, the philosophy is let it crash. Who cares? Which I really like because, in the old days when the server crashed, everybody started crying, managers started yelling at you, the business starts yelling at you, customers are mad at you, things like that. Here, it's like, who cares? The system keeps running. So just real quick, I wanted to kind of cover this a little bit. And what it is just kind of my view of the evolution that we're going through as developers and architects right now, where for a long time we were building monoliths, and we're really good at it. We really know how to do it, and there's marvelous technologies involved with it. Now there's a growing interest in microservices. So the second column here is what a lot of people are doing with microservices, where they're starting to split up the code, but they're not splitting up the data, which is fine. None of these patterns, as I'm going through it, are wrong. I'm not saying that anything is, don't do this. All these patterns are legitimate. But this is kind of the evolution that's happening. So in the third column, kind of showing microservices that now own their own data. So not only have you split the code off, but you split the scheme off. This one's particularly tough, especially in bigger companies. If you're working, like I worked at HP in IT, and breaking up a database is like, whoa. We had data architects and things like that, and that was, I got out of there before this stuff really started to get some traction, and I'm glad I did, because I didn't want to have the arguments about splitting up the database. But I've talked to a lot of customers where they're quite happy with what we're calling a microlith, which is distributed monolith. Where they can break up the code, and they get a lot of benefit from that, but they haven't fought the battle yet with breaking up the database. So anyways, in the fourth column, it's showing, all right, now you're introducing the event log, the write side and the read side. So you kind of really drunk the Kool-Aid, as they say. You're buying into event sourcing and CQRS. And then finally, once you get comfortable with the approach, you're starting to reap some of the benefits. And one of the key benefits I like, what I'm trying to show in that little diagram towards the bottom, all the way on the right, is that the event log is feeding multiple databases. So there's, say it's a relational database, it's a graph database, it's Elasticsearch, 3 different databases that are all consuming events as they occur. They're all eventually consistent with the data, but now you've got 3 optimal, or whatever number of database technologies that are optimal for the kinds of queries that you want to do. This is another reason why I like this so much, because one of the things we tried once before was to have a Lucene, which is the underlying technology of Elasticsearch and so on, database in sync with an Oracle database. And we had it all set up, and we worked very hard on the replication process, and we would get millions and millions and millions of changes in, but every once in a while we'd lose one. And it drove everybody crazy. So we had some very fraction of percent of things that didn't make it, and the customer would see it, the business would see it, our managers were saying, have you fixed the problem yet? And we really never did. I look at this and it's like, okay, I could do this and make it work. So here's just a quick summary of the 6 projects. I'll give you the URLs to the projects in GitHub at the end. But it kind of starts at the bottom with some real simple projects that just show a few Java classes setting and the configuration to set up running something in a cluster. Those are like project 0 and project 1. And then the next project goes into what's called a cluster singleton. And then kind of build up from there. So let me just jump ahead into this. So the first 2 projects, it's actually the second project shows a very simple project, but it's showing an actor that knows how to talk to itself on another node. So there's an actor, if say in this example, I've got 4 nodes running in a cluster. There's one instance of this actor running on each node. This actor knows how to send messages from itself on one node to an instance of itself on the other nodes. And I wanted, in this class, I wanted to show you just some of the mechanics of it. It's pretty simple. And so each of these actors are just, sending each other messages. To me, this is really important because this is kind of the foundational technology for doing some really powerful things. Actors that are cluster-aware, that know how to collaborate with each other across the cluster. You can do some very, very powerful things just with this basic mechanism. So let me show you the project for this real quick. There's a pattern in all these projects. There's a main class that I call runner. And really all this guy is doing is it's setting up an actor system. And this is kind of a test stand kind of a class, but what it's doing is that you can give it a port or ports, and it'll start up multiple actor systems or one actor system. So in the testing I'll show you later on, I normally have like one terminal window, one port, and I'm simulating like running 4 instances of Akka on a single machine, but it's a cluster of 4 JVMs running and talking to each other across the network. The main stuff that's happening here, though, is that this is a line of code for creating an actor system. Pretty simple. It's one line of code. So one way you can kind of think of this is like a thread pool in a way. I mean, it's way more than a thread pool, but it's kind of like that. Because once you have an actor system, the next thing you can do is start up actors. So it's real simple. When you start up an actor, you say actor system actor of, and you give it what a class, and really it's this props method. And this props method is just a way to do like a new with Akka. This is the way to think of it. I won't bore you with the details of it. If you're really interested, dive into this code. But if this class had constructor arguments, then this prop method would take parameters that would be passed to the constructor when an instance of this actor is created. Okay? So the props method kind of gives Akka the class ready to be instantiated. The actor of creates an actor. Okay, and once that happens, the actor is created on this node and it's up and running. So I'm going to show you this cluster listener actor. This cluster listener actor is in all the projects, all 6 of these projects, and it's a simple actor, but setting up an actor is really simple. Normally, the way it is that you've got a class, you're extending some Akka base class. In this case, is an abstract logging actor, so it's a basic actor with a convenience of having a logging set up for it. There's one method that you need to override, and it's this one. So in this method, it's create receive, and what you're defining is what messages is this actor capable of handling. And there's quite a bit of flexibility here, but basically it's just kind of a matcher pattern. And they kind of simulate, this is a little bit nicer in Scala, the way the Scala language works, where you can set this up, but they got it pretty tight on the Java side as well. So with an actor, it's just Java or Scala, but the big difference is that the only way to interact with an actor is no external code directly invokes methods on this actor. An actor, the only way to talk to an actor is to send it an asynchronous message, okay? And I'll show you an example of how a message is sent from, say, one actor to another in a moment. But in this case, what we're defining here is this is the incoming communication channel to this actor. Asynchronous messages coming in. When a message comes into an actor, it handles that message, and when it's done, it just gets the next message. So there's kind of like a mailbox in an actor. While an actor's working on one message, other messages could come in, and they just queue up. And so the actor is just consuming messages as quickly as possible. So it's asynchronous, so the ideal is you're not blocking within an actor itself, because there's some very efficient thread management involved here that happens within Akka. But basically all I'm saying here is that, say when this member up message is sent to me, I'm just going to invoke this member up method, okay? Now this actor is a little different because what I did was I overrode a method that you don't have to implement but is handy Because an actor has a life cycle. It has like a pre-start, it has a running, and it has a stopping kind of life cycle to it. And the pre-start method is invoked when the instance of an actor is created, but before it's accepting any messages. So what I'm doing here is, in this actor, is that I'm talking to the cluster. I'm talking to Akka and saying, hey, I want to subscribe to you sending me messages when the state of the cluster changes. So that's what I'm doing here. All I'm doing is kind of a fun little actor that is logging out. As members are joining the cluster, this guy will see it happen and log it out. When members leave the cluster, this guy will see it happen and log it out. So, for example, with the member up, if I go to the member up method, I just log out what member is it, and then I go to this other method that does a little bit more logging down here. And all I'm doing is that I'm basically looping through, getting cluster information from Akka, which is pretty simple, and looping through it and just dumping out what's the cluster state right now. Is there one node? Is there two nodes? Is there three nodes? So as more nodes are added, this guy sees it happen. It's another powerful feature because this is kind of another example of a cluster-aware actor. As the state of the cluster changes, you can have an actor get messages that you can react to it, and you can do some really cool, interesting things with it. So I'm not going to run this project for the sake of time, which is running out fast. Let me go back to the slides. So that's cluster-aware. So cluster singleton is interesting in that you can define a way to have Akka run one instance of an actor, your actor, in the cluster. There are situations, and often run into this pattern, where you only want to have one instance of the actor running in the cluster. Now, technically, this is challenging because imagine, what can happen here is that this cluster singleton, say, happened to reside on that second node. That second node goes down. Something has to react to the change in the topology of the cluster and start that cluster singleton actor up somewhere else in the cluster. So there's some non-trivial stuff going on here, but this is, again, being built on what I just showed you, things like cluster-aware actors reacting to a state change in the cluster and doing something interesting like making sure that there's a single instance of an actor somewhere in the cluster. This is all built into predefined actors in Akka, but it's not really rocket science either. You guys could write this stuff yourself. You could write your own code that could do cluster singletons, for example. It's not hard, but why do it when somebody's already done it for you? So there's a project that shows just setting up a cluster singleton. I just don't have the time to go into it, so I'm going to zoom past that one. Building on cluster singletons, though, is cluster sharding. And cluster sharding is where we're starting to get into the management of entities distributed across a cluster. So in this simple diagram, what I'm showing is that there's a cluster singleton actor at the bottom that is called the shard region or shard coordinator. And then there's shard region actors. So there's like a proxy, which is a shard region actor on each node. And when you want to send a message to one of the entities somewhere in the cluster, you send a message to the local shard region actor. The shard region actor is the one that has the smarts to know how to route that message to wherever that entity actor happens to be in the cluster. So say, for example, a command comes in to the shard region actor on node 1, but it's a message to an entity actor that's on node 3, right? We don't have to write any code to deal with this. It's handled for us. So we basically just send a message to a shard region actor, and the shard region actor has the smarts working with that shard coordinator to route the message. So our coding is really simple. What's happening is pretty cool because we're just simply sending messages on any node to actors on any other node. Like, so when you're sending in commands, say from a front end, the front end command can come into any one of these nodes, fire off the command to an entity actor, and it'll get routed to the entity actor somewhere in the cluster. So the thing I wanted to get into really is show you the projects that do event sourcing in CQRS. So I blasted through, I really apologize, but just, this is a quick talk, the first 4 projects. But they're all there, and you can run them, and real simple. So what I want to show you is Event Sourcing and CQRS in the last 2 projects. So let me go to those. So this project, this is the cluster, it's called Cluster Persistence, which is the boring name for event sourcing, okay? And this project is a little bit more involved. There's still a runner main, and it's still starting up an actor system. It's doing a little bit more here, though, because really the big thing that it's doing is that it's setting up a shard region. And the shard region is giving us back what's called an actor reference to the shard region actor on this node. So I need that. An actor reference is like a URL to an actor. That's the way to think of it. I'll show you some logging where I actually dump out the actor references. But if you look at them, you can right away see it's a URL pattern. It's like akka.tcp:// blah, 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 okay? Because what I'm doing is I create the shard region actor, which is done here, and this code is setting up the shard region. There's 2 really important things that are happening here. One is I'm telling the shard region what is the entity actor. So I'm giving it the props for the entity actor. So we'll look at this actor in a moment. The other important thing I'm doing is I have to define what's called this message extractor. So let me show you this message extractor. So the message extractor is pretty straightforward. You have to implement 2 methods. It needs to return a shard ID, and it needs to return an entity ID, and it needs to do it for incoming messages. So in this example project, let me show you the entity ID one first. In this method, when it's kind of boilerplate, but sometimes that's what you have to do in Java. But I get a message in, and I just do instance of. Is it a deposit command? Is it a withdrawal command? Is it a query command? And in each one of those situations, I know how to pull the entity ID out of that message. And then basically you're giving that back to cluster sharding that's what it uses to route messages. So when it sees a message for an ID, it's getting the entity ID and it's getting the sharding ID, which is what sharding uses to distribute the actors across the cluster. It's getting these things back, and it's just using it to do the routing. Simple boilerplate code for the most part. So this cluster sharding actor is kind of smart. It's responsible for doing the routing. It has to collaborate with a cluster singleton that's actually deciding where shards are distributed across the cluster. Some non-trivial stuff's happening in there. We don't care. Once we set it up as developers, then the next thing, so I got the shard region actor back, and then I just do I create a couple of simulation actors. One actor is, and I'm passing it the shard region actor ref in the props. So there's the constructor of this actor will take in a actor ref. But I have a command actor and a query actor. So these guys are just simulated. They generate random commands to kind of simulate activity. So let me show you this command actor. There's a couple interesting things that go on in here. Again, it's just an abstract actor. But one difference here is that this actor actually has what's called multiple behaviors. And multiple behaviors is that you can change how an actor reacts to a message depending on the actor's state. So in this case, and this is just my invention as a developer, I said, all right, I'm going to have a sending state and a receiving state. My name, my design. But all I'm doing here is I'm defining what do I do when I see a tick message if I'm in a sending state. And you can see I get a tick message. I'm handling a tick message, and I'll show you what that is in a moment, in both states. But how I react to it is different. I'm changing it. If it's a tick when I'm in a sending state, I go to one method. If it's a tick when I'm in a receiving state, I go to a different method. This is another really interesting way to change the behavior of an actor. You can, it's common to have like almost a finite state machine, and there actually is finite state machine features within Akka itself. But this is kind of a simple finite state machine where, The actor's in ascending state, receiving state, and it's not unusual once you get comfortable with this concept of behaviors to have 2, 3, 4 behaviors in an actor. Some actors have none, really simple actors, but some of the kind of higher level, more intelligent actors often it's convenient to have these behaviors. So let me show you tick for a minute. Back in the old pre-start here, again, this is a method that's called before the actor starts accepting messages. What I'm doing is I'm setting up a scheduler. And what this is it's scheduling to on some interval, these are tick intervals, and it's like a couple seconds, to send myself, self is a method that you can call to get back your actor reference, a message called tick. So what I'm doing here is I just want to send myself a message, this actor a message every interval, right, like a heartbeat. Again, this is a very common pattern that a lot of actors use, some kind of heartbeat thing, it's time to do something, and it waits for a while. It's time to do something, and it waits for a while. So the tick message comes in, and it calls tick sending. Tick sending triggers. Here's an example of sending a message to an actor, okay? The shard region is a actor reference. The method is called tell, and I'm sending it a command. And this command is, I don't have the time to show you this method. This command method is building a random command, okay? It's a random deposit, random withdrawal, random amount, random ID. I'm just trying to simulate activity in this environment. And then it switches behavior. It becomes receiving. That's it. So the idea is it sends off a command and it's expecting an acknowledgement back. So it wants to get the acknowledgement back when it's in a receiving mode. So I'm kind of showing like a timeout here as well, that it's only going to stay in receiving mode for a finite amount of time, and it's expecting that acknowledgement back in that time. And if it doesn't get that acknowledgement back, then it can show that something bad happened. But again, I don't have the time to do it. So the entity persistence actor is the last one I want to show you, is that this guy is a little bit different. It's extending a base class called abstract persistence actor, and this one has 2 different receive methods, or receivers. So one receiver is only used when the entity is recovering its state. So imagine like it's a bank account, and this bank account exists, and we just got a command into it, but the actor wasn't in memory. So the actor is created, and then all the events I'm not using snapshotting here, but if I had a snapshot, I get the snapshot, then I get all the events, fast set snapshot, and I recover this state. That happens very, very quickly, and then the actor's recovered its state. Then it can start receiving commands, which is what I define here. So here I'm just defining, I get a deposit, I get a withdrawal, I get a request for a query. And finally, this is how I handle timeouts. That I haven't received a command in a while, so I'm gonna, the term is passivate myself, or shut myself down, okay? So when I get a deposit command, let me just show you that. In deposit, I persist. This tag command method takes a command and returns an event, okay? So what I'm persisting in is an event. And once said event has been persisted in the sample code it's set up to run with Cassandra, then I call this handle deposit method. So it persists, and then there's a callback method, comes in here, I just make sure I got back an event, and I update my state. And then I send an acknowledgement back to whoever sent me the command. I don't know who it is, I don't care, but I'm sending an acknowledgement message back saying, all right, got your deposit, it's done. Okay? So the sender method tells me, gives me the who sent me the message, and what's the actor reference for the sender. And I just do a tell, and I create an object, and this last parameter, and I say, it's like the return address on the message, okay? And then it fires it back. So running real short on time here, I want to show you something running. So what I've got is, some aliases. It's font small, it doesn't really matter. But I just got a quick way to go into different projects. So I'm going to go into project 5, and I'm going to start up an instance, and project 5, and start up the second instance. Project 5, start up the third instance. Project 5, start up the fourth instance. And let me show you in the logs. So the logging here is these guys, right? It's 1250. All right, so what's happening here is it's starting up. Here's a logging from that cluster listener. And you can see as members are joining, that actor is getting messages and it's logging them out. So first it saw it came up and it saw another member join. Then it saw a second and third member join. And now it should see like all 4 members join. And you can see things like status joining versus status up, things like that, okay? That's all that cluster listener actor is doing. But the more interesting stuff starts to happen. Well, here you can see it's recovering. Some entity is recovering its state. So I've run this in the past. So I've got a local Cassandra instance running. There's some events in there. I only do like 100 entities in this test. So it's just constantly sending random deposits and withdrawals to 100 entities in this example code. So it's running, and then it gets a command and processes it. And you can see there's all kinds of logging in here. You can see the commands coming in, recovering. If you're really interested and you run this for a while, you'll see it actors shutting down because they haven't received commands for a while. And what's happening is there's 4 logs here. So this is happening all across the cluster, right? Command actors are sending off commands. They don't care where the entity actor is. It's going to be on one of the 4 nodes. We don't care, right? The entity actors are getting it. They're processing the command. They're sending back an acknowledgement. It's just another message to an actor. Don't care where it's at, right? So all this is flying across the network between these nodes. So it's things like if I go in and shut down one of these nodes, which I set it up to just where you hit enter, and if the demo guys are with me, it'll shut down. There it goes. Then now I've shut down one of the nodes, but the system's still running. It saw this happen. Whatever entity actors happen to be on that node, when commands come in for those entity actors that used to be on node 1, they're going to be shifted to one of the 3 remaining nodes. We didn't write any code for that. This is being handled by Akka for us, right? So fairly non-trivial stuff happening for us in the plumbing of Akka with fairly straightforward code happening here. So the final project, which I'm probably not going to have enough time to show you, is the last project is what's called Akka Persistence Query. So what's happening there is that it's as these events are going in, there are other actors that are pulling those events from the event log. And in my case, I'm just pulling them and logging them. But you could easily take that code and see where when you get an event, you're going to throw it into your favorite database, which could be, again, relational or Elasticsearch or Mongo or whatever, right? You're building up your read side. So events are happening on one side of the event log. There's a mechanism for pulling that. So the 5th or the 6th project shows you how that's implemented. And normally what I do is I'll run 2 nodes creating, doing Akka Persistence, and 2 other nodes running Akka Persistence Query. But just to wrap up, because we're out of time, and I got plenty of time if anybody wants to talk afterwards. So these are the 6 projects. I know these slides will be shared, but it's on my GitHub, and you can grab them and download them. The first 4 projects don't use Cassandra. The last 2 do. But you should be able to grab them, build them, run them in multiple windows. I'm going to update the READMEs. I've already got some stuff in there, and update the READMEs to, like the one thing you have to handle here is ports if you're all running on the same machine. So 2 of the nodes I started up on like ports 2551 and 2552. And the rest of the nodes, 3 and 4, and you could run more, start up in random ports. But it's all, the configuration works. You can just, like I say, you can grab them and run them. And my goal here was to give you guys something that if you're interested and wanted to see like a full-blown cluster starting out simple and incrementally working up to something more complicated, that you got something to play with. I'm really passionate about Akka. I think you might be able to tell. And I opened my big mouth when I first started with Lightbend, and they said, well, you ought to write a little book about this. So Riley has these, those little booklets that they pass out. So me and my big mouth, I got roped into writing this booklet. But it was a lot of fun. Riley was great as a publisher to work with. It's free to download. You can grab it. It's a quick read, and it's all kind of just no code. It's more of the basic mechanics. If you want to kind of get an understanding of Akka and how actors can interact with each other, things like that, that was my goal in this book. So hopefully, if you're really interested, this is a read. There's tons of other material available on this on the web as well, and books and and whatever. And that's it. I really appreciate your time. Thank you very much. Do we have any time for questions? Yeah, we have some time for questions. Anybody have a question?
Thank you very much. It was really interesting. Looks good, but the question is following. How will Akka react to split brain situation? Because looks like your shard actor, it's like a discovery server in, let's say, microservice architecture.
So I'm not quite understanding the question.
So what will Akka react to split brain situation? When
okay, really good question. So the question is about split brain, and split brain is a really interesting phenomenon in clusters. So what a split brain is that, say we're running on 4 nodes, and a network partition occurs. And what that is that, and say it's like 10 nodes, okay? And say 3 nodes are on one side of this network partition. The network breaks, basically. So 3 nodes are on one side of the partition, and 7 nodes are on the other side of the partition. So the dilemma here is that all the nodes are still up, but it's like the analogy I use, and I did a white paper on split brain as well. It's like being in a conference room, and it's like 10 of us are in a conference room, and all of a sudden a wall appears and splits the room in half. So we don't know we can't talk to, there's 5 of us on one side of the room, and 5 or the wall, and 5 on the other side of the wall, but we can't communicate with each other. We don't know if that wall was a big block that just squished everybody, or are those people still alive? Are they, what? So it's the same thing with Akka. You've got all the nodes that are still running, but they can't communicate with each other. So this isn't part of the open source. It's a commercial offering. There's what's called a split brain resolver. So the split brain resolver, it's cluster aware. So it can see, all the nodes in the cluster can see, oh, hey, wait a minute, we used to be 10, now we're 7. And the other side goes, wait a minute, we used to be 10, now we're 3. And they use that information, and their strategies, and the most common strategy is majority rules. So the 3 recognize that there are only 3 left of 10, and the assumption is that we don't know what happened to the other 7, but we're the minority, so we're going to shut ourselves down. Independently, the other side, say the 7, is seeing the same thing. We're 7, we used to be 10, we decide we're the majority, we're going to stay up. So it's a collaborative reaction, completely cut off from each other. Now, we have an offering to do it, but with cluster aware, people write their own. Okay, so it really is important with clusters, though, is to be able to handle split brain. You have a question back over here?
My question is, can Akka spin out another node? Suppose that we lost 3 nodes, yeah?
Yeah, easily. And this is where things like, what's really exciting is things like Kubernetes, right? So with Kubernetes, say you define the cluster to be n number of nodes. One of those nodes happens to go down, which I heard, for example, that the lifespan of a typical Docker container is measured in days. That say a node goes down and Kubernetes goes, oh, that node's down. I need to fire up another instance to get the cluster back to its defined state. So Kubernetes can handle that, or it could be done manually or some other way. But the nice thing is that kind of at the code level, at the actor level, Akka is reacting to that as well. Oh, I lost a node. Let me react to it until that node comes back. So it can handle a node leaving the cluster, and it can handle the nodes joining the cluster. So another situation might be that dealing with spikes. Say you have a spike that every day in the afternoon you get high traffic. and you have high traffic every weekday afternoon, but you have low traffic other times, and weekends are even lower. So you can add more nodes to handle the capacity, the load at your peak times, and shut down nodes and remove them at non-peak times, right? And now Akka doesn't have any mechanism to add nodes or remove nodes, but it can react to it. So you can build the system so that if you add nodes, it gracefully handles more capacity. Actors start to appear on that node. And if it loses a node, it gracefully handles, oh, I lost a node. There used to be actors over there. Those actors need to be running. There's all kinds of different strategies for bringing those actors up on the remaining nodes in the cluster. So it's really powerful stuff. Any other questions? All right, thank you. It's lunchtime.